So yesterday we spent the first half of class talking about heat transfer and particularly how understanding the boundaries of a system, whether it's open or closed, helps us understand how we might illustrate heat transfer between two objects of different temperatures. We learned that heat transfer eventually stops, known as thermal equilibrium status, where the temperature is the same between the two objects. What that really means is the particles have the same average kinetic energy, because temperature is a measure of kinetic energy. Okay. And then we also analyze how we might draw this out in a particulate diagram via arrows. Since we're talking about energies, we're not talking as much about particles now. We're taking an energy focus. You will be on your test Tuesday, or I think, sorry, did I say Tuesday? I meant Thursday. Your test next week, Thursday, will involve you drawing a particulate arrow diagram to illustrate the stages of two objects transferring heat between one another. So you definitely want to pay attention to the amount of arrows representing the amount of heat transfer and the length of the arrows representing the temperature differences between the two objects. And then after that, we had you guys go into your individual specific heat capacity PowerPoint slide project where you looked at Santa Ynez and Santa Barbara temperature ranges and had to explain why we see Santa Barbara be far more mild and therefore expensive to live in versus Santa Ynez, which is a lot cheaper and a lot more volatile in temperature nature. Okay. So you guys learned about two kind of major subtopics, sub-scientific principles within that to explain, which include energy, heat, or let me put it this way, what affects the amount of heat content something has, and the specific heat capacity of a material. All right. So out of curiosity, prior knowledge from this project, I asked you guys, how does mass affect heat? Okay, remember, heat and temperature are not the same, but they're highly connected. How does mass affect heat? What do we know about? What do we know? Yes. The what? The more mass there is, and how does that affect heat? Do I have more or less heat with more mass? Do I have more or less heat content with more mass? More. So what did you learn from part of this project is that you learned that in regards to heat, okay, which is not equal to temperature. It really is not equal to temperature, but highly connected. Okay. And I don't know why I wrote it so far away. Heat, the more mass an object has, the more heat it generates. So like, for example, if you ever use a thermal camera on someone, I carry a lot less heat than Liam. Okay, Liam, what are you, like 6'1"? Okay, 6'1", 6'2". So there is no way that the amount of heat content that I have is even comparable to the amount of heat content that Liam has. Not because he's moving any faster than me right now, simply because he just has more mass, more particles to generate the heat. Okay. But we also learned separately that something else connects with heat. Something that we already talked about, which is that the more temperature I have, which is like saying the more kinetic energy, the more heat I also generate. They are not the same, but they're highly connected. If I have two objects at the same temperature, but one's larger than the other, the larger item will have more heat. But if I have two objects that are the same mass and one's at a higher temperature, the higher temperature will generate more heat. Relatively intuitive. The biggest mistake people make, though, is that they say heat is the same as temperature. It is not. It is just connected. Okay. So what else did you learn from this project? Something else for helping us understand the temperature ranges between Santa Ynez and Santa Barbara. What else affects heat? Yes. Environmental elements, particularly what about the environmental elements? What about the soil and the water? What were we actually giving value to? Different heat capacities, specific heat capacities. So what is this thing called? Let's go. Don't die on me, little pencil. Okay. Specific heat capacity. We learned that objects with greater heat capacity are able to handle more heat. They're able to handle more heat change, which means they have less temperature change. Okay, a really great analogy for this is human personality. There are some people that just do not respond to stress. They're as cool as a cucumber. Their environment doesn't cause any change. They're really tolerant of stress. They absorb it really well. They take it really well. I am not one of those people. I am a low heat capacity analogous example. I am a low stress example in terms of my capacity to handle shows immediately when I'm stressed. Partly because I have this like super high facial expression issue that I've always had when I was a kid, and my eyebrows like are really like, I used to get teased for how my eyebrows furrow when I think a lot. So I am an example of a low heat capacity analogous material. I change. I show the change quickly. Okay. Roman is not. Roman is a high heat capacity analogous example. I could see it being the case that no matter how stressed you are, you kind of just stay the same externally. Now, you're still absorbing that heat technically. You're still absorbing that stress. You're still experiencing it, but you don't show it. Okay. That's the same idea here, just in the context of chemistry and energy. So then if I have a low heat capacity, right, I just have a way more vulnerable to temperature change. I'm just way more likely to temperature change. That does not necessarily mean I increase my temperature change in terms of I always get hotter. It just means I'm more volatile. I just do up and down a lot. Okay. So specific heat capacity is specifically defined as the amount of heat in joules, okay, required to raise 1 gram of substance by 1 degree Celsius. So the units of specific heat capacity are always joules per grams degree Celsius. This is how much energy it takes to raise a gram by a degree. Per gram per degree. A gram by a degree. Okay? So, a really important conversion factor you're going to want to know is that, and memorize, is that water has a specific heat capacity of 4.180 joules per grams degree Celsius. So to raise 1 gram of water by 1 degree Celsius, I need to input 4.18 joules of energy. Okay. But this also doubles as the conversion factor between calories and joules. Calories is a type of energy measurement. Now, this is not the same calories as your nutritional calories. Nutritional calories is 1,000 little calories, which is equal to 1 kilocal, which is equal to 1 big C cal, which is our nutrition calories. So when it says you have a food item that's like 4 calories, what you're really saying is that it's 4,000 little calories or 4,000 4 kilocal. Capital C calories is your nutrition. Capital C. Okay. But by the way, this is actually though along the same lines of how we figure out why certain food materials are more dense in energy production. Why do certain food materials provide you more ATP to fuel your body when it's broken down? Biochemistry, Krebs cycle, all that good stuff. Okay. This is kind of getting you into that area. Okay. You're going to want to memorize the heat capacity of water, which is also the conversion factor between joules and little cal. And you might also want to memorize that if I'm talking about per gram, it's sometimes helpful to remember that the density of water is 1 gram per 1 milliliter. So that means if I have 25 milliliters of water, how many grams of water do I have? 25. Okay. So that's just something to remember. So practice problems. There's a table on your notes. You're going to answer questions 1 through 3. And sorry about the spacing. It got a little weird. You're going to answer questions 1 through 3 using the table and your previous knowledge revealed in the PowerPoint slides. Go ahead and take that, take about 1.5 minutes to do that. So for the first question, how does the specific heat capacities of metal compare to that of liquid water? What do you notice about the metals? They're all way lower. So metal heat capacities, capital C, little p is the symbol, are way lower than water. Water has a really high heat capacity. It's also one of the reasons that, Earth and living organisms could happen. Without water on planets, not only, of course, do you have not an essential nutrition, but you don't actually have a warm enough environment to promote life. So if equal masses of water and iron were exposed to the same heat source, which one would reach the temperature of 100 degrees first? Which one would change faster, water or iron, and why?
Iron.
Iron. Why, Michaela? Excellent. Iron would change faster because it has a lower heat capacity, which means its temperature changes quicker in response to heat exposure, right? You could write that in response to heat exposure. Okay, so now consider equal masses of iron and water at 100 degrees. Which would cool faster to room temperature? Iron. Jocelyn, can you explain why? Yes, because what it will do is it will respond quicker to the lack of heat. Copy. So iron would change faster because it has a lower heat capacity, which means as the temp changes quicker, its temp changes quicker in response to lack of heat. It will lose its heat to its surroundings faster. The heat will transfer out of it faster. And maybe I should put faster heat transfer / loss. Right? Faster heat transfer / loss. But the one above, it's faster heat absorption / gaining. So this is the start of the scratch of the surface of thermodynamics, of understanding why materials actually respond and absorb heat differently. It's not just because, oh yeah, just because it's easier to cook in a metal pan than an aluminum pan. Or sorry, not aluminum, oxygen pan. Those don't exist. It's easier to cook in a wood pan than some other liquid thing. Or it's instead of being there's no such thing as a wood pan. Well, I guess there is kind of a wood pan, but it wouldn't really work. You kind of burn it. It's disposable. Okay. But what we're really trying to get at is stop for the most part, chemistry is asking you to stop accepting things just as is. Now, there are levels of chemistry that I do tell you guys just to like accept it as it is because it's too complicated. But like for the most part, the posture of chemistry toward the understanding the world is Socratic, like Socratic or whatever, Socratic. There it is, Socratic. It's the why. It's the what am I not seeing? What am I not seeing that's behind the scenes? And can I finally see it? And can I reveal it to others? That's the big idea. So quickly, what are factors that affect heat capacity? Well, we know a couple already. One is the material itself, the nature of the material itself. Okay. That's the obvious one. Another thing that can affect specific heat capacity is the form, the state of matter. So for example, gas water has a different heat capacity than liquid water. And liquid water has a different heat capacity than solid water. Okay. So what I think that's what I'm going to write here is that gas water heat capacity is not equal to water liquid's heat capacity. Yeah, specific heat capacity. Mm-hmm. State of matter. So those are kind of the two main ones that determine heat capacity. All right. That's all I have for you. Now, let me quickly go over that project with you. So, out of curiosity, why does it feel better to stand in wet sand than dry sand? Does anyone have the answer for that? Liam? Okay, so water has a higher heat capacity than sand. What does that mean about me stepping in there then? Yeah, so water has a higher heat capacity than like straight up sand, wet sand, okay? So that means that the wet sand is going to absorb that heat better, which means less heat is going to get transferred to your foot. Okay, so then, Mary, why else can we answer? Does Santa Ynez have a higher temperature range than Santa Barbara?
Because Santa Barbara is much closer to water, and water has a high heat capacity.
Great. Santa Barbara is right by the ocean, which is a vast body of water, which will absorb heat as well as maintain temperature better. It will also hold in the heat better, even if the environment's getting cooler. So what we say then is that the geographical features, the geographical materials of Santa Barbara, okay, higher heat capacity collectively than the geographic materials surrounding Santa Ynez, which is super low heat capacity, which is why, by the way, in the desert, it's super, super hot, desert-like areas, but super, super cold at night. How do we go from sweltering to I'm about to shiver up, right? In the desert, because there's nothing regulating the heat transfer. Not a single ounce of that material is holding in any heat to keep it constant. It's just going in and out like a skeleton drinking liquid. Okay. So if you got that wrong in your CER, you should fix that now. Also, no one shouldn't answer the second question to get a higher extra point. Everyone's capable of answering that. So you guys have about 13 more minutes. If you need to go back and clean up your CER, also, you need to make sure that you have evidence. Please stop writing just generic, oh, the heat capacity. Tell me the value of heat capacity. Don't just write, oh, it has bigger temperature change. Put your phone away. Tell me, okay, the temperature ranges. You calculated them, so tell me them, okay? Even if it's an average of temperature ranges. But stop not using data. You got to use the numbers if I give you the numbers. All right, guys, good job.